Hello friends, good afternoon and welcome to EduSec Live Lectures. Dear friends, today in Computer Sciences we will talk about the concept of data interpretation. To discuss this topic, we have with us our subject expert Dr. Anita Goel. Dr. Goel is Associate Professor in Department of Computer Science in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you. Hello friends, so we will be talking about data interpretation today. So a brief outline of the talk is that we will talk about data and numbers and what is the binary, octal and hexadecimal number system, conversion between data and binary, octal and hexadecimal number systems, and then we will talk about binary arithmetic, addition, subtraction, complements, and then we will talk about fixed and floating point numbers, and then the coding schemes and the logic gates. So let us start. So as you know that data can be of different kinds. It can be a numeric data which can be a combination of sequence of 0 to 9, or alphabetic data starting from A to Z, lowercase, uppercase, or a combination of numeric and alphabetic data, which we also call as alphanumeric data. Also we can have some special characters like underscore and dot, decimal point. All this represents the different kind of data. Now in computers, the computer can understand only zeros and ones. So that means it understands only all numbers represented in the form of 0 and 1. So whatever we write has to be ultimately converted into zeros and ones. So let us formally define a number system. So we say that a number system in base R or radix R uses unique symbols for R digits. So let us say we have a decimal number system which we commonly use every day. So our decimal number system is base 10. Okay, and it uses 10 digits, that is 0 to 9, and when we combine, and we can combine more than one digit to get a number. And what is the base? This is the valid digits that are used to make a number. So decimal number, the base is 10. So we have 10 numbers 0 to 9. Okay, and the position of the digit in a number is counted from right hand side of the number. So the rightmost position of the digit is 0, 0th place, and then the next one is the first place, and so on. Now when we take any number, the digits of the number have two kind of values. One is the face value of the number and one is the position value of the number. So when we talk of the face value of the number, for example, if we have a number named 52, so we have the face value is that at position 0 we have the number 2, and then at position 1 we have the number 5. So the face value is 2 and 5 for the number 52. And if we talk about the position value, so it is base to the power of position. So this is 52 is a decimal number, so the base of the number is 10, and when we say the 0th position, so this is 10 to the power 0, and the position value of 2 is 10 to the power 0, and then the position value of 5 is 10 to the power 1, so which makes 52. So a number is sum of the face value into base to the power of position. So 52 is 5 into 10 to the power 1 plus 2 into 10 to the power 0. So 5 into 10 to the power 1 is 50 plus 2 into 10 to the power 0 is 2, because 10 to the power 0 is 1. So like this we compute what is the value of a number. So when we are talking of number system, so we already know about the decimal number system which we use every day. Then we talk, the computers also understand the binary number system and also the octal and hexadecimal number system. So what we do is we see what are these different kinds of numbers, how they are stored in the computer. So, first we start with the number system which we already know, that is the decimal number system. So, consists of 10 digits 0 to 9. So, any number can be represented as a sequence of digits 0 to 9, for example 34, 8, 6, 7, 3, 2, 1 and so on. Any decimal number may also have a decimal point in it, and digits onto the left of the point are counted, have a position value 0, 1, 2, 3. To the right of the decimal point, the position value is -1, -2 and -3, and the position value corresponding to those positions will be 10 to the power 0, 1 and 10 to the power -1 and -2. So, similarly, when we talk of binary numbers, so we have only two numbers, that is 0 and 1, and the base is 2. So, when the base is 2, so then any number, binary number, is a combination of zeros and ones. And again the same thing, now the position is again counted from the decimal to the left of the decimal and to the right of the decimal. But now we see that the position value changes because now the base has changed. So, the number adjacent or to the left of decimal is now 2 to the, has a position value 2 to the power 0, 2 to the power 1, and to the right it is 2 to the power -1, -2 and so on. Octal numbers, again the base is 8. So, we have 8 digits in octal number, which is 0 to 7, and the combination of these can be represented, can be taken to represent an octal number. So, it means when we are writing any octal number, none of the digits will be more than 7 or less than 0. So, again when we calculate the position value of an octal number, the base changes. So, now the base is 8. So, we have 8 to the power 0, 8 to the power 1 or 8 to the power -1, 8 to the power -2. Now, the hexadecimal numbers have are treated in slightly different way. So, we say that hexadecimal number has base 16. So, there are 16 numbers, but how do we count 16 is slightly different. We have numbers digits 0 to 9. So, that makes it 10 numbers. Then we have A to F, where A corresponds to 10, the letter A corresponds to 10, the letter B corresponds to 11 and so on, and the letter F corresponds to 15. So, the 16 numbers are 0 to 15, where 0 to 9 are the digits and 10 to 15 are the alphabets A to F. Again the position value is 16 to the power of 0, 1, 2 or 16 to the power of -1, -2 and -3. So, these are very basic definitions of the number system and how we relate formally a number to the kind of digits they represent. Now, we see how we can convert a decimal integer into a binary, octal or hexadecimal division, hexadecimal number. Now, a basic common rule is to divide any decimal integer to any other base, we divide by the base to which it is to be converted. So, if we see here, if this example, if we see the first example is where 23 is being converted to a binary number. So, we are dividing 23 by 2 and we are storing the remainder also on the right hand side. And then when we count the when we calculate what is the binary number, so from downwards to upwards we count the digits. So, if we see the first example, so we see at the last rightmost side on the remainder side we have 1, 0, then triple ones. So, 23 in base 10 is 1, 0, triple 1 in base 2. And similarly, if we say convert 27 and 23 into octal, so we divide it by 8 and again we have two remainders 2 and 7, and so it makes it 27 in base 8, and similarly for 16 where we have 1 and 7 in base 16. So, maybe you can try to write your own age in hexadecimal number and see what you get. Now, we have seen conversion of a decimal integer into binary, octal and hexadecimal, but when we convert a fraction part of decimal to binary, octal and hexa, so instead of dividing we multiply. So, here what we do is we multiply, if we have to convert it into binary, we multiply by 2, and octal and hexa by 8 and 10 respectively. And also once we multiply, in the next step we go on multiplying unless we get a 0 or we have performed it 3-4 times, and in the next multiplication we do not consider the non-fractional part. So, let us take these examples. So, we have this number 0.865. So, now we multiply it by 2 and we get 1.730. Now, when we again multiply by 2, so we do not consider the 1 which is the integer part of the 1.730. So, we multiply 0.730 by 2. So, we get 1.460, again we leave out 1 and we multiply 0.460 by 2 and so on. And when we are calculating this value, so we join the numbers upside down. So, when now we see that there is a difference in conversions when we convert a decimal integer or a decimal fraction. When we convert a decimal integer, we divide the number and the remainder is taken from down to up. But when we convert a fraction to any other base, then we multiply the number and we take the non-fraction part from top to down. So, similarly we see that if we convert 0.865 into octal, we multiply, go on multiplying by 8, and if we see, and for hexadecimal we go on multiplying by 16. Now, there is a point to note here that when we are multiplying by 16, so in the non-fraction part we are getting 13.840. So, we do not write 13, but we write the corresponding hexadecimal digit for it, that is D. Okay. So, the value we get is DD7. So, while we are writing the number, we convert the number we get to its hexadecimal value. So, when we are doing a conversion of decimal, so integer dot fraction. So, now if we have any number, any decimal number which may have a integer part, may have a fraction part, or may have both integer or fraction part. So, what we do is we first convert the integer part separately by into the desired base. Then we convert the fraction part separately into the desired base, and then we combine the two parts to get the answer. So, we take one example. So, we have a number 34.4674. This is in base 10 and we want to convert it into base 2 or binary. So, what we do is for 34 we divide by 2 and then collate the remainder down upside, down to up, and for the fraction part 0.4674 we multiply by 2 and then we collect the non-fraction part upside down and then we combine the two to get the answer. So, likewise, so we have seen that any decimal number having a integer or a fraction part can be converted to any other base. Now, the next part is, if you have a binary number or a decimal or a binary number, octal or hexadecimal, you may be required to convert it into decimal. So, this is the reverse of it. So, what we do is, again we have two parts, one is the fractional part and other is the non-fraction part of it. So, what we do is, here what is done is we multiply the number with the base to the power the position value. So, if we see here this slide, so we say what are the steps of conversion. So, we find the sum of face value into from base to the power of position for each digit and start from the rightmost in a non-fractional and from the leftmost in the fraction. So, let us take this example. So, we have this number 1011.1001 in base 2 and we want to convert it into base 10. Okay. So, that is from binary to decimal. So, what we do, taking the decimal point as the focal point. So, to the left of it we start multiplying by raising from the face value multiplied with the position value. So, we have so if we take the integer part of this, so we have 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 into 2 to the power 2 plus 1 into 2 to the power 3, and on the right hand side, that is of the decimal, we multiply by the position value again with the face value. So, 1 into 2 to the power minus 1 and so on, and we finally get the answer. And a similar way is applied if you want to convert from octal or hexadecimal to decimal number. The only difference is now the base has changed. For octal the base will be 8, and for hexadecimal the base will be 16. So, when we are converting a binary, octal or hexadecimal number to decimal number, so we use multiplication only for both the integer part and the fraction part, but it is now the position value with which the face value is multiplied. So, we have seen that we have seen both kind of conversions, decimal to binary, octal and hexa, and from binary, octal, hexa to decimal. Now, we see a third kind of conversion, like we have a binary number, and can we convert a binary number to octal and hexa directly without going through a without converting it to a decimal number? Yes, we can do that. So, what we do is given a binary number, to convert it into octal, we start making groups of 3 bits starting from the right hand side. So, first 3 bits of the right hand side form one group, then the next 3 bits form another group and so on, and for each 3 bit we find the octal number. And for the binary to hexadecimal, again we do the same thing, but now we make group of 4 bits starting from the right hand side, and for each combination of 4 bits we find the hexadecimal number. Now, you may be wondering why the 3 bits and why the 4 bits. Now, there is a reason behind it. See, octal number is represented from 0 to 7, and if we try to write 7 in binary, so that is 111, that is 111. So, that means, and 0 will be all zeros, 0 0 0, 3 zeros. So, what this means is that any octal number can be represented in 3 bits. So, 3 digits are sufficient to represent any octal number. So, when we are making groups of 3, so we will get a unique octal number from that. And why we make groups of 4 in hexadecimal? Because when we say the largest hexadecimal number is 15, and to write 15, so that is 4 ones. So, for first position we have the value 1, second is 2, third is 4, and then it is 8. So, 8 plus 4 12 plus 2 14 plus 1 15. So, 4 bits or 4 bits are required to represent any hexadecimal number. So, that is why we group binary numbers into pairs of 4. So, let us see this example. So, we see that we have this binary number. Now, we partition this number starting from the right. Okay. So, now when you start partitioning, now you see we are converting this to octal number, then we see the leftmost, we are not left with 3 digits, we are only left with 1 digit. So, that is not a problem. So, when whatever digit is there on the left will come as it is. So, when we are making this group, so we made groups of 3 each, and then for each group we find the corresponding octal number. So, 110 is 6, 100 is 4 and so on. So, now the octal number represented is 16546. Similarly, if we do conversion from octal hexadecimal to binary, so we use the reverse step. So, here what we do is we convert each octal number to 3 bits and each hexadecimal number to 4 bits and combine it. So, here is an example. So, we have a number 2BA3 which is a hexadecimal number. So, now how do we convert this into binary number? So, we take for 2 we take 4 bits in binary, for B we take 4 bits in binary, A 4 bits, 3, 4 bits. So, A is value 10, B is value 11, and then we combine all these digits and we get the binary number. Okay, so now we have already done what are the different number systems, how we can convert a number from one number system to another number system, including both the integer and fraction part. Now we do some arithmetic. Arithmetic is like how can we add two numbers, subtract, multiply and divide. Now the computer systems, they actually perform addition and subtraction only. For multiplication and division, some simple operations are performed. So we will not be focusing on that. So we will be focusing only on the addition and subtraction part of it. So before we proceed, like how we add, so there are some rules to be followed. So we will discuss the rules for binary addition. So when we say binary, so we have it means that numbers will be either 0 or the digits will be either 0 and 1. And when we add two digits, what is the outcome? So when we add 0 and 0, it is 0, there is no carry. 0 plus 1 is 1, no carry. 1 plus 0 is again 1, no carry. But when we add 1 and 1, so the answer is 0 and there is 1 carry. If the same rules are applied to 3 inputs, that is we have 3 ones, then the answer is 1 and we have a carry 1. Now these rules are applied when we do binary addition. So what we do is we start adding the bits from the unit column, that is the rightmost column, and whatever is the carry is taken over to the addition is something like what we do in decimals also. If we have to add 22 plus 5, so what we do is 5 plus 2 is 7 and then 2. So similarly we do it here. So let us take a very simple example where we have a binary two binary numbers 1 0 and 0 1. So now what we do is we start from the rightmost side, so 0 plus 1 is 1 and then there is no carry, so 1 plus 0 is 1. So we have this answer is 1 and 1. Now if we have to check whether we have got the right answer or not, so what we do is we see the binary addition. So 1 0 is the decimal number 2 and 0 1 is decimal number 1, and if we add we see 3. So that means we have got the right answer. Now let's take another example. Now here what we see is we have 1 and 1. So if from the binary addition rules, 1 and 1 is sum is 0 and carry is 1. And now when we add the next column, so we have 1 0 1. So the sum is again 0 and then we have a carry 1. So the answer is 1 0 0 and so that makes us 4. So if we do the binary addition, decimal addition corresponding to this, so we see we adding 1 and 3 and the result is 4. So the two are equivalent. Now let us take a slightly different example. So here we have this, so 1 and 1 makes 0 and 1 and 1 makes 0 and we have a carry 1. And then we add this 3 ones, so we have a sum 1 and a carry 1. So now if we take the corresponding decimal, so we see 3 plus 3 is 6, which is this value. Now let us take a bigger number. So if we are doing it same way, 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1. Then we have 3 ones, so the sum is 1 and carry 1, 3 ones, sum is 1 and then carry 1, and then we verify it by the decimal addition. This is another example where we can add more than 2 numbers. So the rules remain the same, that was 1 plus 1 0, carry 1, 3 ones, sum is 1, carry 1, 3 ones, sum is 1, carry 1, 2 ones, sum is 0, carry 1 and then 3 ones, sum is 1 and then carry 1, and this we can verify, and so we have the answer. So we see we can do any kind of binary addition when we are following the binary addition rules. Now we see how subtraction can be performed. So for the subtraction, again we have the same kind of rules. So when both inputs are 0, so 0 minus 0 is 0 and borrow is, there is no borrow. 0 minus 1, the difference is 1 and it has to borrow 1. 1 minus 0 is 1 but no borrow, and 1 and 1 is 0 and there is no borrow. Now again we start from right hand side. The way we subtract is same as we do for decimal numbers. So, let us start with this example. So, we have to subtract 0 1 from 1 1. So, 1 minus 1 is 0. So, we get a 0 and 1 minus 0 is 1. So, we get a 1 and now we verify this with decimal subtraction. So, this is the answer for decimal subtraction. So, let us take another example. Here we have 0 minus 1, but now we cannot subtract 1 from 0. So, what we do is we borrow from the left hand side. So, this becomes 1 0. So, from 1 0 we can subtract 1. So, we get 1 and this is 0 minus 0 0. So, this will be 1. So, this way this is this subtraction is done. So, these are the simple subtraction mechanisms that we have seen, and some complex subtractions and how the borrow is taken are further to be seen. Thank you. So, now we will see some complex examples of binary subtraction. Now, why we call it complex? So, that because now we will have to borrow numbers for subtraction. So, let us see how it happens. So, now if we have this two numbers subtracted, now we cannot subtract 0 to 1. So, we take a number from the left hand side. So, we take this and this becomes 0. Now, 10 minus 1 is 1. Now, again we see left side 0 minus 1 cannot be done. So, again it takes from the neighbor and it becomes 1 0, 1 0 minus 1 is 1. So, now we see again we have 0 and 1. So, again it has to borrow. So, it will borrow again and this will become 10, this will become 0 and then we have 1 and then 0. So, now we can verify this using decimal subtraction. So, basically the rules of subtraction are same as for decimal, but we have to be careful while we are borrowing. This is another example. So, we 1 minus 0 is 1, again for next we have to borrow. So, we borrow, this becomes 0. So, 10 minus 1 is 1, 0 minus 0 is 0 and then again we have all zeros. So, this is a simple subtraction. Now, in this, now this is a long borrow. So, let us see this. So, 1 minus 1 is 0. Now, 0 minus 1 cannot be done. Now, we have to borrow, but we see the two neighbors also do not have any value. So, we have to borrow from the neighbor which has a value. So, how this borrow will be done is, one is it is borrowed to the neighbor and it becomes 0. From here it has to go further. So, from here it becomes 1 and then 10 goes here. From here this again becomes 1 and then 10 goes here. So, this is when we are borrowing from a far neighbor. Now, from 10 minus 1 we have 1, 1 minus 1 0, 1 minus 1 0, 0 minus 1 0, 1 minus 1 0 and we see the corresponding subtraction. So, now we see that if we have to borrow from an immediate neighbor or we have to borrow from a far off neighbor, we can do both and we get the right answer. Now, when we are talking of numbers, till now we have only talked about the digits and the decimal part of it. The another thing is that we can have a symbol also, that is a plus and minus symbol. By default, if the number does not have any symbol, so we treat it as positive, otherwise negative. But in binary numbers, we use the zeros and ones to represent whether the number is positive or negative. So, let us see how we can represent the signed and unsigned numbers. So, in a signed number there are two parts, that is, one is the sign bit and the other is the magnitude. So, the leftmost bit or is called the most significant bit is the sign bit. It is also called MSB and the remaining n minus 1 bits denote the magnitude. So, if we see this, that this is a number, so the leftmost bit is the MSB, the sign bit, and the right is the magnitude of the number. Now, in the sign bit, if the MSB is 0, then the number is considered as positive number. If it is 1, it is considered as negative number. So, when we say consider, it means that the computer understands MSB 0 as a positive number and an MSB with 1 as a negative number. Now, since 1 in a 8-bit digit number, so 1 bit has gone to the sign bit, so there left is 7 bits, and the number of and the amount of numbers, that the range of numbers that can be represented will be minus 2 to the power 7 to 2 to the power 7 minus 1, and the leftmost bit is signed, which indicates that the number is plus or minus. Now, when the number is unsigned, in that case the magnitude can be stored in all the digits. So, that means if we have a 8-bit unsigned number, so the amount of data which it can store is 0 to 255, that is 2, because 2 to the power 8 is 256. Okay. Now, when we have seen how we subtract two numbers. Now, but computer does not subtract the numbers the way we saw just now. Okay. So, what computer does is it uses some simplification to subtract the numbers, and so for this it uses complements, 1's complement and 2's complement. So, what is 1's complement? 1's complement is whatever the digits of the number, each digit of the number is reversed. So, for example, if we have 110, so in 1's complement what will happen? We will have 001, that is 0 is replaced by 1, 1 by 0 and 1 by 0. So, we have several examples where we see that given a number of any size, we can have its 1's complement by reversing each digit of the number. In a 2's complement, once we get the 1's complement, we add 1 to it to get the 2's complement. So, given the binary number 110, 1's complement 001 and 2's complement is 001 plus 1. So, this makes it 010, 010. Similarly, in the next number we see 0100 plus 1, that will be 0101. Okay. And in the next number again we see that we will have 1 in the last, if we add 1 to it, this number. So, basically from any binary number to take the 2's complement, we reverse each of the digits. To take the for any binary number to take the 1's complement, we reverse the digits, and to take the 2's complement, we first take the 1's complement and then add 1 to it. So, this gives us the 2's complement. Now, so what we say is when we are representing binary data, so binary data has a number, a binary number, a position for the sign bit and a binary point, okay, and all this processing is done in the registers, which are high speed storage areas in the CPU. So, there are two ways of representing the position of the binary point. One is the fixed number representation and the other is the floating point representation. Now, if we talk of the fixed point number representation, which assumes that in a number the position of the binary point is fixed. Okay. So, the sign in a positive integer, so when we are representing any number in using fixed point number representation, so we have two things. One is if the number is positive. If the number is positive, then the MSB or the most significant bit will be 0 and the rest of the digits will form the magnitude. Now, if the number is negative, then there are three ways of representing the number. Now, what are the three ways? So, one is that we have the sign bit is 1. So, that shows that it is a negative number, and the magnitude part can be represented in three ways. First is the signed magnitude representation, second is the signed 1's complement representation, and the third is the signed 2's complement representation. So, let us see what this means. In a signed magnitude representation, the most significant bit is 1, but the magnitude remains positive itself. In ones complement representation, the MSB is 1, but the magnitude is ones complement of the positive number, and in sin 2's complement the MSB is 1 and the magnitude is 2's complement of the positive number. So, let us take this example. We have this number 18. Now, 18 can be represented in two forms. We have the positive number 18 and we have the negative number 18. So, if we take positive number 18, so it is plus 1 8. Since it is plus 1 8, so the number is positive, so the sign bit is 0, and then the rest of the 7 digits denote the binary equivalent of 18. So, that is 001 0010. So, in positive plus 18, we have only one way of representing the number. But when we talk of minus 18, so we just saw that there are three ways of representing. So, in signed magnitude, we have the sign bit as 1 and the rest of the number is plus the binary equivalent of plus 18 itself. So, when we see this, so we know that this is a negative number because the sign bit is 1. The second part is representing minus 18 using ones complement form. So, the sign bit is 1 and the magnitude is ones complement of 18. So, when we see the ones complement of 18, this is 110 1101, that is the digits are reversed. And in the signs 2 complement form, we see that again the sign bit is 1 and the magnitude is 1's complement plus 1, that is 2's complement of the number. So, minus 18 can have three kind of representations in a fixed point representation system. So, when the computer generally uses the two signed complement representation to represent the negative numbers. So, generally when we are talking of representing a negative number, so we always by default assume that it is represented in two signed complement form unless stated specifically. So, now the addition of binary numbers when they are in the signed form. So, now we have four possible ways to add two numbers. Either the two number is positive, one is positive, other is negative, one is negative, other is positive, or both are negative. So, the positive number is represented in one form only, the negative number will be represented in two sign form and both are added. If there is any carry out from the sign bit position, it is ignored. So, let us see how this number is done. Now, we will also see how the negative number is taken. So, first we see this addition. Now, in this addition we have taken two numbers, both are positive, that is plus 5 and plus 10. So, now we add these two numbers. So, they follow the simple rules of addition that we did in the earlier class. So, we see that we get the two numbers. Now this is different. Now, we have to add two numbers minus 5 and plus 10. Now, minus 5 is in the 2's complement form. So, you see the first number, the first sign bit is 1 and the rest of the number part of the number is in 2's complement form. Now, we add these two numbers. When we add these two numbers, again using the same rules of binary addition, now what we get is a carry. So, the carry is ignored, the one which we got in the carry is ignored. But now we see one thing, that the result has 0 in the sign bit. So, it means this is a positive answer. So, if we see minus 5 plus 10 is plus 5. So, this is a positive answer. Now, we take the reverse. So, we do plus 5 and minus 10. So, we see when we are adding, the second number has a sign bit of 1 and then it has the 2's complement of 10. Now, when we add these two numbers, so now when we are adding again using the same rules of addition, so now we see that the leftmost bit of the answer is 1. So, that means this number which we have got is a negative number in 2's complement form. So, we have to convert this 2's complement number into a positive number. So, one shows that it has to have a negative sign and the rest of the part is again converted into the magnitude part. So, first we take the ones complement and add 1. So, we convert these number in back into its base form. Now, these are two where we have -5 and -10. So, both numbers have MSB as 1. So, they are negative numbers and the rest of the magnitude is in 2's complement form. We add the two numbers again using the same rules of binary addition, and now we see that we have a carry which we ignore and we have a MSB which is 1. So, it means this is a negative number because -5 and -10 is -15. So, this is a negative number. So, again we convert this number back into the base form, so that we get the answer 15. Now, this is addition of two numbers. Now, when we want to subtract two numbers, what do we do? So, when we want to subtract these two numbers, so what is done is that we change the sign before performing the operation. So, let us see this. So, if we have plus say minus, we have to subtract two numbers. So, what we do is we say plus a is plus a and minus of plus b is we add minus b. So, we convert b into the 2's complement and add the two numbers. So, likewise we see that any kind of subtraction between two numbers can be done by changing the sign of a particular number. So, we are always adding two numbers and changing the corresponding sign of the individual number to take it in 2's complement form. So, this makes subtraction very easy. So, using a single operation of addition we can also subtract. Now, the second is the floating point representation. In a floating point representation, so first was the fixed point representation which what we were talking till now. So, this is the floating point representation. So, it uses two registers. Like fixed point representation assumed that there is a fixed position for binary point. Here what it does, it stores the number without the binary point in the first register, and the second register stores the position of the point in the first register. Okay. So, now because of this the number is divided into two parts, the mantissa and the exponent. Mantissa is the signed fixed point number and exponent is the position of the binary point. So, if we represent this number, so we have this number plus 110,011.11. So, now this has a 8-bit mantissa and 6-bit exponent. Now, if we try to represent this number, so what we do is first we do it mechanically. So, now we bring the decimal point to one of the ends. So, when we bring it to one of the ends, so this number becomes 0.1100111 into 2 to the power 5. Now, we have to represent this into a mantissa and exponent. So, the mantissa is first is the sign bit which says the number is positive. So, it is 0. The second part is the mantissa which is the point after the value after the expression, the decimal point, and finally 5, 2 to the power 5. So, the 5 is represented as in its binary equivalent form, that is 000101, and these number of digits is we are taking that 8-bit mantissa and 6-bit exponent. So, these are 8 digits in mantissa and 6 digits in exponent. So, the number can be floating point numbers can be represented like this. So, now we have talked about the numbers, the conversions, the number systems, the conversions from one number system to another, both the integer and the fraction part. We also saw arithmetic, binary subtraction, finding the 2's complement form, 1's complement, 2's complement, adding, subtracting, and how the number is stored in the computer. Now, we see some coding, binary coding schemes, like we have different kinds of data and combination of bits, and the bits are grouped in a fixed size. Based on this, different coding schemes are designed which represents a unique combination for different symbols. So, we have basically commonly used 3 coding schemes. One is the ABCDIC, ASCII and the Unicode. So, we see what these coding schemes mean. So, we have the ABCDIC, which is extended binary coded decimal interchange code. So, this is a 8-bit code which has 4 bits for zone and 4 bits for the digit. And so, since it is 8 bits, so the number of combination of unique combination of digits can be 2 to the power 8. So, that is 256. So, using the abscisic code you can represent 256 unique symbols. Now, this is generally used in mainframe computers. Nowadays, we use the ASCII code, which is American Standard Code for Information Interchange. Now, there are two types of ASCII code, ASCII 7 and ASCII 8. ASCII 7 is a 7-bit code where you have the 3-bit for zone and 4 bits for the digits. So, so total 7 bits make is 2 to the power 7, that is 128 combinations. So, you can uniquely identify 128 different symbols. Now, this was later modified by IBM for ASCII 8. So, now ASCII 8 has 8 bits, 4 bit for zone and 4 bits for digits. So, you can represent 256 unique symbols using this, and it is widely used in computers. Now, lately, so when we say ASCII code 256 digits, so we have 0 to 31 for some control characters. Now, some of the few ASCII codes which you should always remember as a computer student is that number 0 is ASCII 48, capital A is ASCII 65 and small a is ASCII 97. So, if you know these three, you can find any other. So, if you know capital A is 65, so capital B will be 66, capital C will be 67 and so on. If small a is 97, so small b will be 98, small c will be 99 and so on, and 48 is 0, so 49 will be 1 and so on. So, these are some of the key ASCII numbers that you can remember. Now, next is the Unicode. Now, Unicode is relatively quite a new standard which has been, it is a universal character encoding standards. Now, the problem with this ASCII and abscisic were that the maximum number of digits that you could, symbols that you could represent were 256. Now, there are so many languages, each language has so many different kind of symbols and they all have to represent it uniquely. So, those coding schemes were not sufficient for that. So, Unicode scheme is used so that you can use text, symbols, characters, multilingual environments, and the range is, so it is a 32-bit code. So, it means you can represent 2 to the power 32 unique symbols, which is quite a big number. It comes to almost 4 billion combinations. So, most of the computers today support Unicode, and to make it compatible with ASCII codes, the first 256 codes of Unicode are same as the ASCII code. So there is no compatibility problem as such, and it is implemented by the character encoding. So, UTF-8 is the character encoding which is used, and it uses 8 to 32 bits. So, if this is one of the common, so if you see MS Word or any word software, so you see you can use different symbols nowadays. So, you can choose any symbol, and if you see down that you will see the character code of the symbol, and you will also see that it is a Unicode in hexadecimal. So, you can see the code of the that is, for example, in this symbol inverted U. So, here we see that the character code is 2229 and this is in hexadecimal. So, different kind of characters can now be represented when we are using Unicode, different languages, and this has got a longer list. If you scroll down, so you will see that quite a few characters can be represented using this. So, this is all about coding. So, we now come to the next part which is the logic gates. Now, why we talk of logic gates, we are talking of number system, we say binary number system, our computer works on the binary number system, but actually how does it work on the binary number system, who adds the numbers and who does that. So, for that hardware electronic circuits are there, so that input is given to them and then the relevant output is produced. So, we have these basic gates AND or NOT, and a combination of these basic gates NAND, NOT, XOR and XNOR. Now, we see this, so we know AND is where the two numbers are, we get a output when both inputs are true, that is when if both inputs are 1, we get the output as 1, otherwise the output is 0. In OR gate, we see that if any one of the inputs or both the inputs are 1, then we get a 1, we get a 0 only if both the inputs are 0. In a NOT gate, it reverses it, if the input is 0, the output is 1, if the input is 1, the output is 0. And we see the NAND gate. So, NAND gate is a combination of AND and NOT. So, what is it? First, if you see the first symbol, part of the symbol, it is the AND symbol, and there is a small circle at the end of the symbol. So, at the end of the curve of the symbol, so that is the NOT. So, what it says is first you do the and then NOT it. So, if now both the inputs are 1, so the AND will give you 1 and then the NOT will give you a 0. So, if both the inputs are 1, the output will be 0. So, basically whatever is the output of a AND gate, a NOT of that is the output of NAND gate. Then we see the NOR gates. So, again the same thing, we see this OR symbol and then we have a small circle which says NOT. So, whatever is the output of the OR gate, we NOT that output, that is complement that output to get the output of a NOR gate. In the XOR gate, what happens is, XOR is when both the inputs are different, then only we get a 1. If both inputs are same, we get a 0. So, if both inputs are 1, still we get 0. If both inputs are 0, we get again a 0. If they are 1, 0, then only we get a 1. And XNOR is whatever we get from XOR, we NOT that output, so or complement that output to get XNOR. So, now one of the tasks for you could be that can you design truth tables for these gates, and I think you should try that. That will give you more insight into using these gates. So, friends, today we have seen all data representation, the different coding schemes and how arithmetic can be performed using it. Thank you. Thanks a lot.
Dear friends, we hope that with today's lecture you have come to understand the concept of data interpretation in a better way and you have been benefited by it. On that note, we would like to thank Dr. Anita Goyal for coming here and delivering this wonderful lecture. And thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.